Great, recording.
Okay.
Welcome.
All right, so let me continue. The next, I think, to me, very useful result is called the Schwarz theorem. It's actually useful if you want to get to modular forms. So what it says here is, start from the case here. It's we are talking about particular. Hey. So I need to connect my point. Sorry, it's not connected. Anyway, so what I'm trying to say here is it's referring to the case where the multi-set alpha consists of two elements. So only two parameters. Now it's called A and B. And the lower parameter is 1C. And then the variable will be Z over here. Schwarz theorem says that now if you have two independent solutions to such a homogeneous differential equation near zero, and what you can do is you take a ratio. When you take a ratio, basically you get a mapping which sends the upper half plane, which is marked as pink, and the lower half plane, which is white. The upper one will be mapped to a triangle. And in particular, it sends the singularities 0, 1, and infinity to the image of under the Schwarz map to D0 and to D1 and to D infinity. And then there will be kind of wrapping around originally on the line over here around 0. The upper half plane is kind of flat, so forming an angle pi, and will be mapped to pi. P pi over here. P is computed as 1 minus C. Okay? And so for near 1, the angle is going to be Q, which is C minus A minus B. It's the special exponent near 1. Infinity, the angle will be A minus B. So what you will get is from the upper half plane, what you get to is a special Schwarz triangle with pi, P pi, Q pi, and R pi. They computed from the parameters. And if you look at the universal cover of this triangle on the right-hand side, there are 3 situations. And if the P plus Q plus R is bigger than 1, what you get to will be the sphere, CP, so it's a CP1. If it turns out to be exactly 1, it's going to be the universal cover will be the Euclidean plane, which is C. And more commonly, it will be when P plus Q plus R is less than 1. The universal cover will be the upper half plane. So let me get to a special case over here. So it's one example in which the monogeomic group is a finite monogeomic group. When it's a finite monogeomic group, a feature of that is you can write down the corresponding hypergeometric function as an algebraic function. So in this particular case, we can compute the PQR using the formula in the previous page. For instance, P is 1 minus C, so it's 1/2. Q is C minus A minus B is 1/3. And then R will be the difference of these two. So what you will see is you get to the upper half plane is mapped to a triangle. And then wrapping around this point, you need 3 of those upper and lower upper half planes putting together. So you need 3 copies of the combination around the North Pole. And then down here, you need 2 copies and 2 copies, or 2 copies here. So you get to the universal cover, which is a sphere. And the corresponding hypergeometric function is algebraic. So then that leads us to the notion of triangle groups. So assuming the same kind of setting, plus we are going to assume that P is going to be 1 over either an integer at least 2 or infinity. In this particular case, what we can do is use the refraction. For instance, in this picture, I have the upper and lower half plane met into this particular triangle. if we use the refraction for P corresponding to this edge in the middle, we can do a refraction around this corresponding edge. We get to an isometry of upper half plane. In this particular case, of course, refraction is not orientation preserving, so we need products of them to get to something which is orientation preserving. So you use these three generators. So one is GP, attained by product of two refraction. When you raise to E1 power, because of the nature of how it's obtaining to, you get to the identity. So now we get to the triangle group with exponents E1, E2, E3. Under the assumption the angle is 1 over E2, 1 over E1, E2, E3 times pi. So we get to the triangle group. So which is a subgroup of the isometry group of the universal cover. And in particular, we're interested in the case when the universal cover is the upper half plane. Right? So we said that such a group is arithmetic. This is going to be a notion generalized, the notion of finite in the subgroups of SL to Z. Okay, so this notion is defined to be arithmetic if the group gamma is commensurable with non-one group of certain quaternion order. And then it's by the classification of Takeuchi. There are 85 arithmetic triangle groups. Divided into commensurable classes, there are 19 of them. So for some of the cases like 2, 3 infinity, this is the classical example. The group is isomorphic to PSL to Z, so there are cusps. And some other groups like 2, 3, 6, 6, this is actually the case. The fundamental group will be entirely lie in the upper half plane. So when you're doing the identifying the boundaries, it's already compact. So when the modular curve is already compact, when you're identifying the corresponding boundaries, it's called Shimura curve. And the Shimura curve, according to Shimura, they parameterize abelian variety, abelian surfaces, two-dimensional abelian varieties, admitting quaternion multiplication referring to the group, which is described by 366 that here we consider that as a non-one group of the quaternion order. In particular, for 366, the quaternion algebra in the background will be 3 to Q. All right, that means there are basically it's going to be a rank 4 algebra generating by I, J, and K, and I squared is minus 3, J squared is 2, and then IJ equals to minus JI. And my colleague Fan Ting Tu and Yifan Yang have been studying quaternion orders extensively. So if you have questions, you could ask them. Okay. All right.
Is this group finite? This 366?
Infinite group. It's infinite group. Yes. You can, if you ask Fan Ting, she will tell you how to write it down in terms of matrices. So matrices inside invertible matrices with entries in one square root 3, like Q joining square root 3. Yeah.
Okay.
So one natural questions we would like to ask is, we know that 366, like 366, according to Shimura, it's actually classifying two-dimensional abelian varieties with quaternion kind of multiplication, in a sense there is a operator I, operator J, I squared is minus 3, J squared is 2, right? So, and we know that we can come up with such pictures using the hypergeometric background. So when we started in 2014, the question is, can we use hypergeometric kind of the perspective to construct abelian varieties parameterized by, say, 366. Right. So it actually led us to one of the collaboration out from Women in Number 3 conference. took place in 2014. The result, kind of surprisingly to us, is as follows. Basically, we looked at the cases when there is an integer which is either 3, 4, 6, so that the Euler phi number will be 2 for those cases. And if we have IJK, they are integers within the range of 1 and n minus 1, and satisfying the property that the fixed one does not divide any of the combinations. This is some non-degenerate kind of assumption. Then we can get to a curve, which is of the form that it's going to be ramified cover, unfold cover of CP1, ramified at 4 points, 0, 1, 1 over lambda infinity. And we can use the Jacobian of this curve. In particular, it depends on the nature. We can look at the primitive part, because if I have a divisor of this superscript, the divisor will be a quotient. And then if I take away something which is in primitive, we look at the primitive part, we get to a two-dimensional abelian variety parameterized by lambda. And the funny thing is, in the end, if we want the two-dimensional abelian variety constructed in this very kind of rough description, maybe I will give you more details later. And the endomorphism algebra of this two-dimensional abelian variety contains a quaternion algebra. If and only if this two beta quotient to be algebraic. Right? So that turns out to be a very clean answer. All you need to compute will be this two beta ratio. And then you look at the quotient and see whether it's going to be algebraic. Right? For instance, if we specialize this 6 n to be 6 over here, ijk to be 4, 3, 1. So we get to one parameter family of two-dimensional abelian varieties, whose endomorphism algebra contains this quaternion algebra that we mentioned. And then there is a different construction using Picard curve by Peckovier and Schicker.
Ling, if I may jump in here with a question. Supposing, do you have a generalization of this theorem if I want a quaternion algebra over a totally real number field, for example, q adjoins square root of 5? Is there a generalization of this theorem?
I think there's a generalization of this theorem. Yes, it's basically the idea later when we understood better is to look at the period matrices.
Okay.
And then look at
one little comment in this Takeuchi list. Of course, he talks about quaternion algebras not only over Q, but over any totally real number field. Okay.
Yeah.
And if you take it over, say, a real quadratic field, the abelian varieties don't have dimension 2, they have dimension 4. Okay.
Exactly.
So yeah, so it isn't just two-dimensional abelian variety. So
right.
It's interesting to me that if you, of course, for n equal 3, 4, 6, you're going to get quaternion algebras over Q. Right.
Yeah. Yes, I think if you check into higher cases, this number will go up to 4 and higher. But I mean, I think the method basically is go back to computing the periods from the value of hypergeometric functions that may still kind of apply to the other constructions, but we did not pursue further. Okay, now let me get to wrapping everything to this is a very nice example, which is a very special Schwarz map. Right. So the Schwarz map I'm going to use is going to be correspond to the upper parameter to be 1/2, 1/2, lower parameter to be 1, 1. And for this particular case, you can check that, of course, down here, there is a solution. Another solution you can use is when you change alpha to 1 minus alpha, it will get you another solution. It's due to the symmetry between the singularity 0 and 1. And it's also kind of an exercise to check that the one up there is not holomorphic. So it's not scalar multiple of the one below. In fact, if you take a ratio of these two solutions, you put the I to the front to make it onto the upper half plane. This is actually a classical example. Go back to Ramanujan. You will get to the inverse map of the modular lambda function, parametrizing elliptic curves with level 2 structures. All right, so I'm going to dig into the backgrounds of this particular Schwarz map a little bit. And the corresponding picture over here, it actually maps the upper half plane to one of the triangles. So this is the upper, this is the lower one. And it's drawn to this way, so you can see there are 6 copies relating to the fundamental domain for SL2Z. So gamma 2, it's actually the modular curve is a 6-fold cover of the modular curve for SL2Z. So with that said, let's get into the backgrounds of this mirror map over here. Then we're going to spend some time on the Legendre curve. The Legendre curve basically is the protocol for a lot of things that we have been done. So it's actually written as y squared. So lambda is going to be a parameter, which is going to be, you can fix that to start with as long as it's not 0 and 1. And so it's going to be double cover of x, CP1 parameterized by x. So you have CP1 parameterized by x. And then it's ramified as 0, which is corresponding here 0, 1, 1 minus lambda, and also the other ramification occurs at infinity. So it's a double cover. To get to the picture, what we're going to do is perform the branch cut along any 2 singularities, all right? We just happen to choose the branch cut along 0, 1, and 1 over lambda infinity. If I perform the cut, I will get one of the two up here. The cut will kind of split into a loop 0, 1, and then similarly, the red one will kind of cut into 1 over lambda and infinity. We use 2 copies of that, so we group them together. So you see that we get a torus. And in this particular picture over here, once I get to a torus, of course, we can compute the first homology group. If I compute the first homology group, naturally I have this one, the loop 0, 1, which is corresponding to the cup. The other one I should mention here is you can actually connect 0 to infinity. If you connect 0 to infinity, you mark it as blue. You see that it corresponds to this particular kind of cycle, which is another generator for the first homology group. So what I want to say is later when I want to compute the periods, which will be the coupling between differential forms and homology group, the generator for the homology group can be composed from the branch cuts. All right, that's what I want to say. So now for given lambda, if I look at this elliptic curve, then we all know elliptic curve up to scalar, there is only one differential, holomorphic differential one form. For this particular case, it's written as omega lambda, which is dx over square root x, 1 minus lambda x. All right, so this is the homology group I mentioned. There are 2, one corresponding to the loop around 0, 1. The other one is 0, infinity. With that, with the 2 players, you have the holomorphic differential form, you have the first homology group. You can look at the period matrix, the period lattice. The period lattice will be the z kind of span of the integrals of your holomorphic differential form along the 2 generators. You do the linear span. And if you pick a different basis, it doesn't change too much. So it's up to the corresponding Schwarz map is different by a matrix inside gamma 2, all right? And up to relabeling, we can assume that the ratio over here, it's lying in the upper half plane, okay? And that's why we get to the kind of the meaning for the Schwarz map when we introduce in the Ramanujan's result. Okay, so before we get back to Ramanujan, there is some of the questions I would like to bring you to the attention. The first question is how likely this ratio, such ratios in general, turn out to be very transcendental by nature, right? So if you want to ask how likely the p-adic ratio is going to be algebraic, the answer is quite unlikely. For the generic precision, the ratio is going to be transcendental. Right? So it's actually a fundamental result by Schneider that this ratio is going to be algebraic if the corresponding Legendre curve admits complex multiplication. And then it points to the Charles-Selbert period, which is tied to one of the results by Nesterenko that I mentioned earlier. So Charles-Selbert formula tells you that if you have an elliptic curve, which is admits complex multiplication by this imaginary projective field with fundamental discriminant minus d, then all the periods of this elliptic curve, they are algebraic multiples. So, which means either one that you're talking about, the first period or the second period, they're all algebraic multiples of a gamma product, gamma value products. And the first one is gamma 1/2, which is square root pi. The second one is very much like the recipe in Nesterenko's kind of formula. So it's gamma of A ranging between 1 and d minus 1 as the numerator into a fraction with denominator d. It could be in the exponent could be plus and minus depending on the values when you put into the Legendre symbol. In addition, that you put you compute how many root unities, which is n over here inside this imaginary quadratic field, and then dividing out by 4 times the class number. Right? For example, using this formula, you can compute omega minus 4 will be this quantity over here, while omega minus 3 will be this particular quantity over here. Right? So you're going to see that the very extreme case, you get to the CM case, the periods, the transcendental part has been described very explicitly by the Charles-Selbert formula. Okay. And then the next thing is the notion of pick-up-foots, which will be very important later for us. It's why we get to algebraic varieties. It's through the connection of pick-up-foots equation that I first picked this up from Noriko Urich many years ago. Right? So what is the pick-up-foots for a given family of algebraic varieties? Essentially, for our setting, what we're going to see is how we're going to type everything back to the parameter set, which is alpha to be 1/2, 1/2, beta to be 1, 1 for our case over here. So essentially, we're going to vary the lambda. So this is a differential 1 form. So we can let lambda vary. And then we also vary the 2 cycle. One is 0, 1. One is going to be corresponding to 0 and 1 infinity over here. So we're going to also vary the cycles on, this is H1 of L lambda Z. So we're going to vary the 2 generators analytically. So as we vary lambda, we get to the integral. Now it's not as a single complex number, but it's going to be a function of lambda. Right. So now, what is the pick-up-foots? The pick-up-foots basically is going to be which differential equation when you apply to, the value is going to be 0. And for our case, essentially, the pick-up-foots equation will annihilate the differential omega lambda, which is dx over square root x, 1 minus x, 1 minus lambda x. Applying the differential operator, what you will see is you get to a exact form. So you get to something which is exact. So then when you're taking an integral around any closed loop, because of this is the exact form, what you get is a 0. All right. And for the Legendre curve, we know that this is going to be the correct differential equation, because if you apply this differential operator to this differential, you get something exact. All right. And later in my lectures, I'm trying to outline if you looking at varieties in your family, all right, then if the line later turns out to be hypergeometric, then your point counts can be used. Very often you can use hypergeometric functions over finite fields. That's what I'm trying to kind of convey over here. So putting things together, we see that now it's going to be this period function. It's a solution for the hypergeometric differential equation. And again, there are two solutions. One will be this holomorphic one down here. The other one will be this particular one with a log solution. So the ratio, if you put in this way, putting an I over here, it will turn out to be the inverse of the lambda function. So that this particular example actually encodes a lot of kind of things I'm going to explain in the remaining two lectures. Okay, any questions before I kind of trying to wrapping my lecture up and move on to the next topic? Any questions? Okay, so let's continue. So for the remaining of this kind of lecture, I'm going to spend time to talk about hypergeometric formulas. And what made hypergeometric kind of functions attractive to me? One of the major reasons, of course, there are many available formulas already in the literature, so we can use them if we know how. All right. So for example, one of the there are many examples. Let me just give you a few and mention how we can attain them. For example, this is one quadratic formula. I think it's by Kuma. It's a quadratic formula in the sense that on the right-hand side, it's a function of x. On the left-hand side, it's a rational function of degree 2, right? So it's actually a formula that you can prove by using rigidity. It's easy to write down the Riemann schemes on the kind of the right-hand side. So what you would do is the same as before. You write down 0, 1, infinity. And the local exponents near 0 will be 0, and then b minus c, etc. So you write down the corresponding kind of the Riemann scheme on the right-hand side, and then you're going to look at the Riemann scheme on the left-hand side. You can check that they are the same, all right? If they are the same, it means one thing. Both functions are solutions inside the same solution space. They will be annihilating by the same differential operator. Right. The other thing, of course, if they're inside the same space, there's still some freedoms. The other thing we're going to check will be the local behavior near x equals to 0. And conveniently, the right-hand side starts from 1 and plus higher terms. The same thing happened to the left-hand side. So the agreements of these two behavior near 0, the local exponents at 0 will be the same and start from the same kind of formal power series extension, tells you they will be the same function. Right. So this is the method which is by rigidity. And in the background, what we can see is actually if you look at the corresponding kind of Schwarz map, and if you look at this picture on the right-hand side, and the angles, as what we said, one will be C minus B. Another will be C minus B minus C. Okay, the other one, which will be this angle down here, okay, which is 1. The other one will be B minus C. Okay, one have, the other ones, okay, So you can write down the corresponding PQR, all right? So 1 will be 1 minus C, so 1 minus C minus B plus 1. So you get to C minus B. And the other one will be B minus C, will be the difference between the upper parameters. So you have B minus C, which is this particular quantity over here. Okay, the other one will be here. The other one will be C minus B minus A. So then you will actually get to this is going to be the mapping for the corresponding Schwarz triangle. And the one on the right-hand side will take only half of it. So the relation in between will be more or less in terms of monogenomic groups, all right? This group, the corresponding to a bigger group, the one on the right-hand side corresponding to an index 2 group, all right? This is one of the informations in the background. And then there are also other techniques that we also outlined in the lecture notes as well. Some of the techniques, including one of the very kind of direct ones from definition. If I want to compute 2f1, ABC at 1, we just use directly, this can be written as the period function dividing out by the normalizing factor. If t equals to, when the argument is 1 over here, I have 1 times t, so these two parts can be put together. So it can be written as a beta function, all right? And it can be evaluated in terms of a gamma quotient, so it's gamma C minus A minus B over gamma C minus A and gamma C minus B. And this one is called the Gauss evaluation formula. It's very innocent looking. However, surprisingly, this innocent looking formula is the feature more or less like J function. You know the values at rho, you know the values at I, you know the value at infinity. Then modular equation allow you to compute J values at other imaginary quadratic points. So this is more or less playing the fundamental role for one of the CM values, right? And other technique, including you can actually conclude such an identity is true by looking at, for instance, this one, again, you can use the rigidity. And once you know this is a kind of agreement between two hypergeometric functions. To get to the next one, the idea is now it's very simple. As two formal power series, they are the same. That means when I do the formal power series expansion, the left-hand side and the right-hand side will be the same as well, all right? So if I expand the coefficient on the right-hand side, I get to this expression for the nth coefficient. So this is the nth coefficient here. And the coefficient, the nth coefficient on this hand side will be relatively simple, will be this expression. So then you get to the next formula, it's called the Pfaff-Schulz formula. It looks, again, it's kind of very innocent looking. However, this is one very useful evaluation formula, allow you to derive more and more identities. So these are the basic building blocks you can use to derive many, many more wonderful identities, all right? So the other kind of technique I want to mention will be specializing values in no identities. For example, if I get back to Kummer quadratic formula, and if we specialize the value to the right-hand side to be 1, we know that then I can evaluate this one by the Gauss evaluation formula. And when I put the value into 1 over here, the right-hand side, if I put, let me see, did I put in the wrong way? If I put 1, it's a trouble. Okay, it's actually when I put minus 1. All right, so let me redo everything, sorry. If I want to evaluate at minus 1, Okay, what I did is actually put the -1 into the left-hand side, then I get 4 on the top. I get 2 square, which is 4 in the bottom. So we get to value 1, right? And so what I'm trying to say that the Gauss evaluation playing a fundamental role, we give you a reference point how to derive other CM values more or less, all right? Then the left-hand side can be evaluated by Gauss. Then you can actually write down the formula down here. And from here to there, use a double angle formula for gamma functions. So you get to the right-hand side. It's kind of funny, then this formula tells you what happens at the very special value, which is -1 now, which is not 1. All right. It's very often, depending on the parameters, it's going to be a CN value. All right. And then the very last formula, I'd like to spend a little bit more time on that. It's obtained by other methods. For instance, it's one of the methods called Bailey transform. All right. And the Bailey transform, of course, is after Whipple. Whipple attained this formula around, I think, 1925. So in a paper, he wrote down several formulas for well-posed theories at value ±1. So for this particular example, left-hand side and right-hand side both have value 1. It's well-posed in the sense that if I add a and the 1 down here, I get a plus 1. If I add this 2, again, I get 1 plus a. If I do the same thing, I get 1 plus a. All right, so the left-hand side is well-posed. And another feature about the left-hand side is for sure it's not primitive. So it's in primitive. Primitive. Okay. In the sense that if you look at this A2 and B2, so you have A2 to be 1 plus A over 2, B2 to be A over 2. The difference is 1, it's an integer. So it's in primitive. So for this formula, Whipple said that this 7f6, it turns out to be related to the right-hand side, which is a 4f3. So to me, this means there is some degeneracy. You go from some structure which is more complicated. In terms of iterated integral, you need to put a lot more iterated integral to get to the left-hand side. The right-hand side is greatly simplified. So in terms of iterated integral, I only need 3 layers. All right, so there is a degeneracy structure relating 7f6, which is a well-posed series in primitive, into some structure which is actually easier. Right. So for kind of one of my project with Winnie Lee and Fountain 2, we dig into what's the geometry behind this picture and how to use that to construct Galois representations which are decomposable, all right, which is one of the motivations. There is something which is degenerate into this particular formula telling me something happened if I putting things out according to the recipe on the left-hand side, guaranteed something decomposed. One piece of that will be the right-hand side. All right. So maybe I will get to that later. All right. So with that said, I think I finished most of my materials prepared for today's lecture. So going back to kind of wrapping things up, I just want to say that in a classical hypergeometric world, there are hypergeometric functions, differential equations, modular representations, Schwarz maps, a lot of things going on. And our key motivation is how to apply all those beautiful formulas you can obtain in many different ways into understanding the arithmetic of algebraic varieties, such as the Legendre curves. Okay, so we'll move on to finite field settings tomorrow. Okay, thank you.